Greetings, everyone. Learning is a hobby here. I wanted in this video to go over section 1.3 in elementary cryptanalysis by Sinkov. So I'm going to go through my notes. This is a very short section, so this video should be kind of short. And I want to show you guys a nice resource that you can use to do some of the things that we'll be doing in this book. So let me bring up my notes. And actually, before I even do that, let me just say, I know it's been a while since I posted videos because I've been working on my Patreon page, which you should check out. I'll have a link in the description bar. And work has been kind of, a little bit hectic, but I have a little bit of time now. So for the next couple weeks, I think I'm going to try and make a post every day here on the YouTube channel to make up for the lack of videos in the recent past. So keep a lookout for that. I got all the books over here. I'm working on the chapter summaries for the next sections here. I want to get back around to Schifrin, and of course I'm really looking forward to doing chapter 5 and Spivak, so keep an eye out for that stuff. I'm gonna try and really make an effort to get a video posted every day, at least for the next couple weeks. So anyway, let's get to the video for today, though. Let me bring up my notes. Okay, so chapter 3 in Sinkov is about additive alphabets, one of which we've seen already, which is the Caesar cipher. The Caesar cipher is an additive cipher. It's a cipher that uses an additive alphabet, with the key being the number 3. So you add 3 to all of the if you label the numbers A through Z as 1 through 26, if you add 3 to each of those and then replace them back with the letters that those numbers correspond to, you get the Caesar cipher alphabet. So it's just basically a linear shift by 3, right? So, but there's nothing special about the number 3. So the Caesar cipher is an example of an additive alphabet. It uses a linear shift of 3. There's nothing special about the number 3. However, in fact, Caesar could have used a shift of any number except for multiples of 26, because that would leave the message unchanged, right? You'd come back around to the same alphabet. If you were using the English alphabet, obviously he wasn't. I don't know how many letters there are in the Latin alphabet. I should have probably looked that up beforehand, but you get the idea, right? If you were using the English alphabet, then you don't want to use a shift of a multiple of 26, because that leaves the alphabet unchanged. So plus there are other things that Caesar could have done that would have made the Caesar cipher even more secure. Like they could have agreed, both parties, communicating parties, on a number beforehand, or they could have sort of used the message itself to pick a number to say to the other party, the decrypting party, what the number should be. Maybe you would count the letters in the note, or maybe you would use the date as the number, or modulo 26, or there's many other schemes that they could have picked, but this was what they call the Caesar cipher. So we're going to look at general additive alphabets here. There's only 26 additive alphabets because there's only 26 ways you can shift an alphabet, an ordered alphabet that has 26 letters, right? You can either not shift it at all, or you could shift it by 1 or 2 or 3, et cetera, all the way up to 26. So, or all the way up to 25 rather, because 26 would be the same as the no shift at all. So, all right. If a plain text alphabet and cipher alphabet are related by a linear shift, meaning adding or subtracting a number, modulo 26, we call that an additive cipher. Okay. If P is the number representing the plain text letter, then the number for the ciphertext letter corresponding to P is given by the formula C is congruent to P plus K, modulo 26, where K is the key. So K is the number of places that we shift the plain text alphabet to get the ciphertext alphabet, right? Modulo 26. Okay. Like I said, this is kind of a short chapter, but there are some things I wanted to show you. So there are many, actually, many mechanical devices that exist to allow for easy encipherment and decipherment of additive ciphers, as well as monoalphabetic ciphers in general, which we'll get to in a later section. For example, the cipher wheel. I have a photo of an example of a cipher wheel, which I'll show you in a second. The way that a cipher wheel works, which I just realized as I'm recording this video, I actually have an example of a cipher wheel that I should have dug out of my desk somewhere. I have it. I don't know off the top of my head, but maybe I'll show it to you in the next video because I don't have it on me right now. But I do have actually an example of the cipher wheel. But anyway, I have a picture that I can show you here. The plain text alphabet is written on the outer circumference of the wheel, and the inner wheel contains another copy of the alphabet, but may be rotated to achieve a setting which gives any of the 26 additive ciphers. Let me show you a picture of what that means. I think if I share my screen, you should be able to see this. So this is an example of a cipher wheel. So the alphabet that's on the outer perimeter is the plain text alphabet, and notice that the inner alphabet you can rotate, and it looks like it has holes here, so you can like lock it in place. So that you can place, if you want to make for example, the Caesar cipher, you would replace. Sorry, you would put next to each other the letter A on the outer perimeter. The letter under it would be the third letter, which would be, what is it? D for the Caesar cipher, right? +3. This one is not actually, let's see. This one's not actually additive. This is reverse additive, because if you look, the alphabet is not the cipher alphabet here is written backwards. So I think actually the U.S. Army in the past, way in the past, used cipher wheels like this, where it was an additive alphabet, but not just an additive alphabet, it was a reversed additive alphabet. So you had permutation, a specific permutation of the letters, you just reverse the order, and then you could make on top of that a linear shift. That's what this represents here. So you would, like I said, the way it works is you would locate A on the outer wheel, which in this one you see over here. So, and then you could move, the inner letter here is, if that's N, then this gives you the cipher alphabet, for example. But you could twist it so you can change the settings. And like I said, I actually have an example of a cipher wheel, which I'm really disappointed that I forgot that I had that because I could have showed you how it worked in the video. But that's fine. In the next video, I'll remember to bring my cipher wheel out so I could show you how it works. Anyway, that's an example of a mechanical device that helps encipher and decipher additive alphabets, or like I said, monoalphabetic ciphers in general. Another such device is called the Visionnaire Square, which I have a picture of as well over here. I'll show you the Visionnaire Square. I'd have to share the screen here. Okay, this is called a Visionnaire Square. So notice that you have the plain text alphabet written on the top of the square, and also to the left-hand side of the square. And then if you look, you have all 26 linear shifts listed underneath each other. So you could, for example, you could call the Caesar shift by the letter that starts out on that line, which would be D. So the Caesar shift would be line D, right? If you wanted to do a shift of 11, you would pick L, and so on like that. So here, this is the Visionnaire Square is already, all 26 shifts that you can have are already written out here for you. There's other uses for the Visionnaire Square for more complicated ciphers, for example, polyalphabetic ciphers, which I'll show you a little bit of in a second, but I don't want to go too much into that because he has a whole chapter on polyalphabetic ciphers, so I won't talk about that too much here because we'll stick with monoalphabetic ciphers for now. But this is what the Visionnaire Square looks like, and it's it's a useful tool to have, as you could just have it near you while you're enciphering or deciphering, and it makes it easy to do that. All right, so let me stop this share and go back to my notes. Okay, and then finally he says there are two essential elements to a cryptographic system. One is the general procedure, the general system. Here we've been looking at additive ciphers. That's the general procedure for these types of systems. And the second important part is the specific key. So for example, for the Caesar cipher, the specific key is 3, and it's the general system it's an additive cipher, right? In general, if you only use one alphabet, it's called a monoalphabetic substitution. So all of these ciphers, those 26 ciphers that we looked at, those additive alphabets, those are all considered monoalphabetic substitutions because we're only using one cipher alphabet to encrypt. All right, but you can have multiple alphabets. Like I said, that's called a polyalphabetic substitution cipher. That's something that we'll look at later on, not in this video, but later on in the book. So okay, and then we have the exercises. So this is the fun part, right? These are relatively easy problems because we haven't gotten to cryptanalysis yet. These are just, he's describing these types of systems. So, the exercise there's two exercises for this section. Question 6, part A says, construct the additive alphabet for the key 7 and encipher the message. So, hang on, I got a cough. Let me pause the. Sorry, it looks like I'm coming down with a cough again. This is the message default. Dear Brutus is not in our stars, but in ourselves. What you want to do, I'll let you pause your screen. You can try this. So make an additive alphabet with the key of 7, and then encipher that message. So you could line up the alphabets, and then you could use that to encrypt. And then I'll show you the solution in a second. All right, so what I want you to do is pause your screen and try it, and then when you finish, come back and unpause. All right, so let's take a look at the solution then. So here's the alphabet with the key 7. So this is an additive alphabet with key 7. So the blue alphabet is my plain text, and the red alphabet is the cipher alphabet. So it's a shift of 7. All right, and if we encrypt using this system, what we do, for example, to encrypt the letter T, this one here, you go to T in the on the plain text alphabet, and you use the red letter instead. So that T encrypts to A, and H, for example, encrypts to O. E encrypts to L, and on like that. So that gives you the encrypted message here. So AOL, MHB, SA, etc., etc. Right, so you can check to make sure that you did that correctly. Okay, and there is one more problem in this section. So here it is. So here they want you to decipher this particular monoalphabetic cipher, knowing that it's an additive alphabet with key 11. So first, set up your cipher system. So write your plain text alphabet, then your additive alphabet underneath it, your cryptographic alphabet, your cipher alphabet with key 11, and then you can use that to decrypt this message. So pause your screen, give it a try, and then I'll show you my solution. Okay, so let's actually go through the solution. All right, so this is the cipher system here. Again, in blue, I have the plain text alphabet, and in red, I have the ciphertext alphabet, and we can use this to decrypt. So for example, E, whoops, sorry, I have to go backwards. So if I go to E on the in the red alphabet, that decrypts to the blue letter, which is T. If I go to S in the red alphabet, that decrypts to H, and on like that. So if you just, go through the whole message here, decrypting, you get that the message is, there is a tide in the affairs of men, which taken at the flood leads on to fortune. So hopefully you were able to do that. And that's basically it. Like I said, it's a short section. But there is one more thing I wanted to show you before I end the video. And that is, there is a nice tool that you can use online. Hopefully you can see this. Did I share the screen correctly? Yeah. This is Simon Singh's website. Let me just promote his book real quick before I show you this. Simon Singh is a mathematician, and he actually has a whole book on. It's meant for lay readers, but it has some puzzles in there and everything. It's called the Code Book. It's on the history of cryptography, which is a really fun read. This is a good book to bring with you on a trip or something, because it's fun to read through on the plane or whatever. But he also has a website devoted to cryptography. So let me bring that back up and show it to you. Okay, so he has all these ciphers here that you can use. Notice that before I show you the monoalphabetic thing here, you have Visionnaire Square over here, and he has a Visionnaire Square in tool that I'll show you how to use in a minute. But I want to start just by showing you that how to use the monoalphabetic cipher. So let's say that we want to encrypt something. This will do it really quickly for you. You have for additive alphabets here, you actually have to put it in by hand, the cipher alphabet, but it'll pick. So if you say randomized cipher alphabet, it'll give you a general permuted alphabet here. But let's say that we want to use that. Oops, how do I? Let's say we wanted to use that alphabet that we just used in the last problem, so that with a shift of 11. So you would type it in manually, which is a little bit more tedious, but it's not that bad. Sorry, the lighting is here making it hard for me to see the keys on my keyboard here. Sorry, just bear with me while I put everything in. Okay, so now I have the cipher alphabet inputted, and now let's say I want to encrypt. What was the thing? There is a tide. What was it again? There's a tide in the affairs of men or something. Which at the flood, I forget what it is. There's a tide in the affairs of men, which taken at the flood leads to fortune. Oops, how do I go back? Here we go. Which taken at the flood leads to fortune. All right, so say I want to encipher that message, and you can choose to keep the spaces between words or not by just unclicking this feature here. So you click on encipher plain text, and it gives you the enciphered message right over here. All right, and you can also use this to decipher as well using the same alphabet. So if you type in if you type in the ciphertext that you have and type in the correct, cipher alphabet with the correct key and click decipher plain text, it'll decipher the message for you. So it's kind of a neat tool to have, makes some of the tedious features of decrypting and encrypting a little bit easier to handle, because it's it does all the drudgery work for you. So this is a nice tool. I'll put a link to this down in the description bar if you want to check it out and play with it, because he has all kinds of ciphers on here that you can play around with. And I just want to show you real quick that you could do this also with the Visionnaire Square tool. But this tool here is not as convenient to use for a mono-alphabetic substitution, because you need to use a keyword, because the Visionnaire cipher, like I said, is a mono-alphabetic substitution, which we haven't talked about yet. So for example, here he has the keyword as example. So if you want to use that as your keyword, then and you press update keyword, what it does is it chooses the alphabets from the Visionnaire Square, where the lines, it picks the alphabets that you use, using the words, the letters from the keyword. So notice he has example written here. These are the rows in the Visionnaire cipher that start with those letters. So what the Visionnaire cipher does is it uses more than one alphabet. So for example, for the first letter, it would use the first alphabet, E. For the second letter to encrypt, it would use the second letter, X, the alphabet denoted by X, and so on and so on, and it just keeps repeating like that, until the message is completely encrypted. So it uses multiple alphabets, which is useful for certain things because it hides certain structure in the message that is inherent in the language that's being used, particularly letter frequencies. But we'll talk about that more in depth when we get to more advanced stuff. But you could still use this if you wanted to do a mono, a linear shift. Like for example, if we wanted to do the shift of 11, you could just type in a bunch of L's here and then use that as the keyword, and then it'll, let's say we want to do, what is it, there is a tide in the affairs of men, taken at the flood. Leads to fortune. Right, so we can encipher, and you see that you get the same thing. The only difference here is it doesn't leave the spaces between the letters, but you still get the same encryption here. So you could use this as well. In some ways, this might be more convenient because you don't have to input the you don't have to put the alphabet in by hand into the boxes if you're using a linear shift. But yeah, I don't know. Fool around with it and see what you think. I think it's a pretty neat thing that he offers on his website. So like I said, I'll put the link to the Black Chamber down in the description bar if you want to play around with it. Let me stop the screen share for a second. So I'll see you guys in the next video. I'm working on, like I said, I'm going to try and do a video each day for the next couple weeks or so. So I got Spivak, Schifrin, Taylor, Axler, and Simmons coming up relatively soon. So I'll see you guys in those videos. Do me a favor and check out the Patreon page, and I'll see you guys in the next one. Until that time, keep learning, everyone.